All right, what's up, class? Ready to do part 2, I guess. So we're starting from number 9 now. Yeah, okay. So for this one here, algebraically, make sure you know that when you've got a binomial in the numerator and a monomial in the denominator, it is perfectly fine to kind of split that and just re-express it as a over c plus b over c. It's actually sort of obvious that that's okay if you think about it in reverse. If you had a over c plus b over c, you would notice that you had a common denominator. Of course, you could combine them in that way. It is often useful for us to break it down in this way. And what I don't want you to do is think that the same thing holds true when you have a monomial in the numerator and a binomial in the denominator. A lot of people run into a trap where they think they can say that this is a over b plus a over c. That is, of course, nowhere near to true, because again, imagine trying to reverse that. We would need a common denominator, would multiply by c over c. This would get multiplied by b over b. There's your common denominator. That would be an AC plus an AB all over BC, which is just pretty clearly not the same thing that we started with. So trying to simplify that way is never going to be okay. So get that out of your head this instant. But keep this in your head this instant because it's useful. What am I doing? Lock. And then I'll shrink this, wait, up. Okay, shrink that, and we'll keep that around, but move it to there. Okay, so that's our first step then. We see that this could be rewritten as 1 over tan squared. It's debatable whether or not you should bother showing this step. If you wanted to go directly to cotangent, you certainly could. There's no debate. There's no point really in showing tan squared x over tan squared x. I'm doing that because I'm the teacher and I want to make sure you guys are understanding every little step I take. But it would be perfectly fine for you guys to go sort of directly to the 1 over tan becoming cotan and the tan over tan becoming 1. And then, hey, guess what? I bet that's a Pythagorean identity, and it, of course, is. What would this be? Cosine over sine. So we've clearly divided the original function through by sine squared. So that means this should all equal 1 over sine squared, which is cosecant. Actually pretty easy to remember that. The alternate form that has a cofunction in it, cotangent, the other function is the other cofunction, cosecant. So we know this would boil down to cosecant squared. So there's your simplified form. What about our restrictions? We said in class that tangents in the denominator are a little bit tricky. Because if you think about it, this is a 1 plus tan squared. But our denominator now is technically a fraction too. It's a sine squared over cosine squared. So that means if we let cosine be 0, we'll be dividing by 0, will be undefined. But if we let sine squared be 0, then our whole denominator will be 0, and the whole expression will again be undefined. So when you've got a fraction in your denominator, it doesn't matter which part of that fraction is 0. The whole expression will end up undefined. So we know right away that our original expression has restrictions that say that sine cannot be 0. Cosine cannot be 0 either. And then clearly our simplified form is 1 over sine. So we already have incorporated into the rule that sine can't be 0, but we're going to have to add extra restrictions that say x cannot be the values of x that'll make cosine 0. Cosine is x, so that's pi over 2 plus pi k. And if you're starting to think that our restrictions are always either pi over 2 plus pi k or just plain old pi k, well, you're right. So far, that's been true. There are other problem types, obviously, that might have some different restrictions. I don't know if any of them made it onto this worksheet, though. We'll find out. Let's do 10. Hard to decide what color to use. Let's use orange. All right, 1 minus sine squared is cosine squared. We all know that. Maybe we don't. Hopefully we do by now. Okay, so I'm here. Really like to think about dividing by essentially a fraction. I'm going to go ahead and put that in, I guess. This is a cosine squared divided by cosine over sine. The cleanest way to think about this for me is that dividing by a fraction is multiplying by the reciprocal. So to me, our numerator cosine is actually getting multiplied by sine over cosine, which is tangent. And then we can cancel the cosine with one of the cosines. And this is another somewhat unsatisfying one. We end up with a final expression that's just cosine times sine. But you can't do any better than that. So that's it. Again, this expression here, cosine has a domain of all reals, sine has a domain of all reals. So that means any restrictions on the domain of the original will have to be listed as restrictions. This function has no restrictions at all. So any restrictions from here, this expression will have to inherit them. And we do have restrictions. We just talked about having a fraction in our denominator. So we know that cotangent is cosine over sine. So again, sine cannot be 0, or else cotangent will be undefined. And if cosine is 0, then cotangent will be 0, making the whole expression undefined, because again, you'll have division by 0. So this is another expression where neither sine nor cosine may be 0. So that means our exceptions, our restrictions would be that x cannot equal, what could it possibly be? If sine can't be 0, then it can't be here or here. If cosine can't be 0, then it can't be here or here. So this means we have to exclude all 4 positions. So it would be 0 plus pi over 2, which means just pi over 2k. So as soon as I address this thing as always coming up, we now have a slightly different one. But that'll do it for 10. Looks like I'm looking at 2 Pythagorean identities, right? We should know by now that it's tan squared plus 1 equals secant squared. So subtracting the 1 would give secant squared minus 1 equals tan squared. So your numerator is tan squared. You can just directly make that substitution. It's sine squared plus cosine squared equals 1. So we can see that someone subtracted cosine squared to get sine squared equals 1 minus cosine squared. That denominator is sine squared. Okay. Again, perhaps the cleanest way to think about this is a sine squared x over cosine squared x all over sine squared x. That's a complex fraction. If you don't like the way that feels or looks, then maybe just up here, this is just a tan squared multiplied by 1 over sine squared. And then if you think about it like that, we can more cleanly see that, okay, so this complex fraction really is sine squared over cosine squared multiplied by 1 over sine squared. So really, instead of expressing it as a complex fraction, we can just say, okay, we've got the tan squared fraction by quotient rule. It's getting multiplied by 1 over sine squared. That, of course, would be the same as dividing by sine squared. So, you know, whatever gets you here, you can now see that those cancel cleanly. You get 1 over cosine squared. That's secant squared. And we're done. It looks like we're finally ready to have some different restrictions in our lives. Looking here in the numerator, secant is a reciprocal function. It's 1 over cosine. So we know right away that if cosine of x were allowed to be 0, secant would be undefined. then we do have a denominator. This entire denominator cannot equal 0. That means if you add cosine to both sides, we know that cosine squared cannot be 1. We haven't seen that yet. And then we'd also have to take the square root here, and we would find that that means cosine cannot be plus or minus 1. So suddenly what we've got are actually 3 restrictions on the cosine function that are going to generate restrictions on our angle measure x. This is different. This is new. That's it though, right? We don't really care if secant equals 1 because zeros in the numerator are fine. Zeros in the denominator are bad. But that's our deal. So have we lost any of those restrictions as we come down here? Well, if we're still secant, then cosine still can't be 0. That's already known to us. That's already evident. But these restrictions, we're going to have to list them. So where does cosine equal plus or minus 1? Well, draw yourself a little unit circle. Remind yourself that cosine equals x. And so x is positive 1 here. X is negative 1 there. And very uninterestingly, even though the restrictions on our function have changed, the restrictions on our angle are not really different. It's just 0 and pi again, 0, pi, 2 pi, 3 pi. So it's going to be pi k. Okay, so that covers everything in my opinion. Let's do 12. I think I'm happy with that. Let's do 12. 1 plus cotangent squared is cosecant squared. Everybody knows that by now because you've been studying, paying attention. You've already done 11 practice problems, so you know it by now. I don't have to explain it. I refuse to. So our numerator is cosecant squared. That's a Pythagorean identity. In the denominator, we've got a cotan and a cosecant. So clearly, before we do anything else, we can just cancel out a cosecant. We now have cosecant over cotangent. As I alluded to before, that means we might think of this as a cosecant x. Instead of dividing by cotangent, let's multiply by the reciprocal of cotangent, which is tangent. And then from here, it's probably a little cleaner to proceed. Instead of a complex fraction, we just have the product of these two. It's just going to be a fraction times a fraction instead, which probably feels nicer. So what is this? 1 over sine? And what's this? Sine over cosine? And guess what? Those cancel. So you're looking at 1 over cosine, which is secant. Uh-oh, I failed to change colors between steps. It's a faux pas. You can be orange. So there's your final version. There's your simplified version. What is the domain of the original function? Well, in the numerator, we've got a cotan, which is cosine over sine. So we know that if we let sine be 0, we would be undefined. So we will not let sine be 0. In the denominator, we've got another cotan. So that still means sine can't be 0 or cotangent will be undefined, but it also means cosine can't be 0. Because when cosine is 0, cotangent is 0, then our whole denominator would be 0. We've also got cosecant. Cosecant will be undefined. Cosecant's 1 over sine. So sine can't be 0. We've already hit that. We've already addressed that. So that's it. This is the full list of restrictions on the domain of the original function. There's nothing new, nothing even out of the ordinary. These are the exact same restrictions we've seen 12 out of 12 times practically. So like, what about down here? Secant's 1 over cosine. So again, the domain of secant already stipulates that cosine cannot be 0, but secant would allow for sine to be 0. So that means we have to say, hey, yeah, no thanks. No thanks on sine equaling 0. And when does sine equal 0? Sine is y values. Y values are 0 here and here. So we need to exclude those positions on the unit circle, which are 0 plus pi, 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 pi. So pi k. K is an integer. All right. So there's your simplified function with extra restrictions heaped upon it. Moving on. So what are we going to do here? My heart says get a common denominator. Cosecant is 1 over sine. So we're looking at a cosine squared over sine x plus sine x. And maybe we've seen exactly this, just in a, I think we have had a problem that started here. So we're just seeing a slightly different starting point. So if you think of this as being over 1, we would want to generate a common denominator. So we'd multiply this term only by sine. Well, technically what's happening is you're multiplying the denominator by sine x. And of course, if you want to do that in the denominator, you have to do it in the top as well. So it's sine x over sine x. That leads us to cosine squared x plus sine squared x. There's your Pythagorean identity. And it's all over sine x in the denominator. So this should feel familiar to you. We've done this before. This is now just 1 over sine, which becomes cosecant. There's a simplified form, not too hard. So now, oh, right, restrictions. Cosine has a domain of all reals, sine has a domain of all reals. So we see the only factor that has any restrictions at all is cosecant, which is 1 over sine. So sine must never be allowed to be 0. And guess what? Cosecant already has that restriction on it. So I would say we're done. It's that expression. No further restrictions are necessary. All right, sweet. Let's do the next one. That's looking like a Pythagorean identity to me, right? Secant squared minus tan squared. It's a slightly different form, so I'll run you through my thought process again. I always just start from sine squared plus cosine squared because I know it so well. I know I'm not going to screw that up as a starting point. I know I want to arrive at the function that involves, or at the identity that involves tangent. So sine over cosine is tangent. So I know I'm dividing through by cosine. So that shows me that tan squared plus 1 equals secant squared. Yes, I'm using shorthand here. I think that's fine because this isn't real work I'm showing. This is sort of scratch work. It's like I'm doing this in the margins or off on scrap paper. I don't have to be all formal. But anyway, so secant squared minus tan squared. Oh, okay. Subtract tan squared from both sides. And you see that secant squared minus tan squared is 1. You don't really need to commit these alternate forms to memory. You just have to be quickly able to do the algebra to derive those alternate forms. That's my opinion on the matter. I know some other teacher would probably push for you to do, like, to actually memorize. I just don't think it's worth it. Block. I'm going to take all this. I'll let it stay, but I'll shrink it down really small. We'll put it in the corner. All right, so guess what? That means I can right away just turn the entire numerator into the number 1. And again, a little rule of algebra here. I talked before about A over B plus C, which we said you can't really simplify at all. You can't do anything with that. But that's not what I have. I have A over B times C. So can that be thought of as, okay, bad example, super psych. If this was a 1, could you break that down? Think of it as a 1 over B times a 1 over C. Yes, absolutely. Because 1 times 1 would be 1, and the B times C would be BC. So I can take that and break it down into 2 separate fractions. And so that is exactly what I want to do. because then I would just have those reciprocals. So this becomes 1 over tan times 1 over cosecant. And you wouldn't necessarily show that step. 1 over tan, of course, could directly become cotan, while 1 over cosecant just directly becomes sine. And then by quotient rule, this is cosine over sine, getting multiplied by sine. So if we thought of this as over 1, you don't have to do the over 1, of course, but we see that those cross reduce, leaving us with simply cosine x, which is kind of good news in the restriction department because we know cosine x has a domain of all reals. So any restrictions on this thing's domain will have to be inherited down here. So what are our restrictions? In the numerator, secant is 1 over cosine, so you better not let cosine be 0, or else you'll have division by 0. Tangent is sine over cosine, so you can't let cosine be 0. In the denominator, sine over cosine still, so you can't let cosine be 0. Cosecant is 1 over sine, so finally we can add sine not being 0 to the list. And again, don't forget, we can't let tangent be 0 either, but that's still sine over cosine. So you can't let the numerator be 0, so that sine can't be 0. But again, and I'm starting to get a little bit bored of this, but it's the same exact restrictions we keep having over and over and over again, where neither sine nor cosine can be allowed to be 0. Again, just remember, that's all 4 positions. That's all 4 quadrantals. So if we need to now list those as restrictions, comma, x may not equal, it's going to be 0 plus not pi k, but pi over 2. Pi over 2 is what's going to push you to all 4 positions. So pi over 2k, where k is an element of the set of integers. So there's your simplified function and your restrictions. And finally, we get to the last 2. All right, how do we do it? The temptation is to distribute the cotan, and maybe that's a good idea. I don't know. Let's see. If I turned everything into sine and cosine, this would be 1 over cos. This would be cos. This would be cos sine. So again, I'm just kind of quickly and informally checking to see what's smart here. If I distribute this in, what will I have? Cosine squared over cosine, so that would be cosine. If I distribute this in, I'll have cosine squared over sine squared, which is super psych. I'll have cotan cubed over sine squared. Not loving that. That feels weird, so that seems to tell me that that's not the way to go. So if you don't want to distribute, then you probably want to simplify what's in parentheses first. And what's in parentheses is something we've seen before. We've got 1 over cosine. We don't have a common denominator. So let's get a common denominator. Leave cotan alone for a while. Our common denominator would be cosine, so you'll multiply this by cosine over cosine. That's going to give you 1 minus cosine squared in the numerator and a cosine in the denominator. Okay. Guess what? Guess what 1 minus cosine squared is? It's sine squared. So this can become sine squared over cosine squared. At which point I would go ahead and use quotient rule. This is now cosine squared over sine squared. Yeah, that's right. All right, and now we can see things cancel nicely. The sine squareds cancel. This cosine cancels one of the cosines. We're left with a cosine in the numerator. So cosine is our final and simplest form. And again, that's good because this function has no restrictions. which means any restriction from up here needs to be inherited and listed it down here. So yoink. What are our restrictions? 1 over cosine. So cosine shall not be 0. Cosine is fine. That's all reals. Cotangent is cosine over sine. So again, we have that sine cannot be 0 either. If sine was 0, cotan would be undefined. If cosine was 0, secant would be undefined. So we've got those same exclusions. Literally, this is going to be the same as 14. So you'll have to stipulate that x cannot be pi over 2k. Okay, is an element of the set of integers. All right, one more. Okay. If you were to instantly just distribute cosine, it wouldn't cancel anything out with sine. It wouldn't cancel anything out here either. So it seems like a bad idea. Seems like I should leave it alone. So cosine, you'll wait on the outside while we clean up the inside. I got a sine x. I'm adding to it. Well, cotangent is cosine over sine. So this is cosine squared over sine. This is the same old thing. Put this over 1. Get a common denominator. This becomes sine squared x over sine x. That's cheating, but I'm doing it anyway because I'm getting sick of this. We've got a cosine on the outside. This becomes sine squared plus cosine squared in the numerator. That's 1. And this is a sine x. So rather than turning this into cosecant, though, notice that when you multiply by cosine, you'll have cosine over sine, which is cotangent. So it might be worth noticing, though, that that does in fact mean that cosine x times cosecant just directly becomes cotangent. That might be a factoid worth memorizing. And then from there, it would stand to reason that sine of x multiplied by secant of x, well, guess what? That's sine times 1 over cosine. That becomes sine over cosine, which is tangent, right? So these are nice little mini identities worth memorizing. What did we just say? You become cotangent? What did you become? Tangent? These also happen to be nice little rules that link all the co-functions and all the non-co-functions. Cosine, cosecant, their product is cotangent. That's kind of neat. Sine x times secant, their product is tangent. That's kind of neat. So you might want to memorize that. I'm sure those will come in handy. But then again, if you use that in your, as you show your work, I might get all mad and say, you haven't shown enough work. I would kind of rather see you break things down to sine and cosine and take smaller steps as you do your work. But it's not like I could take points away from you or anything. This is certainly a valid thing. And if you memorize it, more power to you. It's a shortcut that is certainly fair and justified. Anyway, here I am. What are my restrictions? Nothing, nothing, nothing. And this guy, whose only restriction is sine shall never be 0. And cotangent, guess what? That already has those restrictions. So I, again, would say no restrictions necessary. Again, remember, I'm saying no further restrictions besides those things that are already naturally restricted from the domain of cotangent. For me, the restrictions are the things that are not already evident from the function. So I say we're done. All right. Yeah, great. See ya. We're done. Bye. Have a great one. Adios. Great. Bye.